Voronoi diagram. So we use an example to illustrate how the Voronoi diagram works. So the Voronoi diagram will partition the problem space into the discrete segments. Remember what we can return from the Voronoi command in MATLAB is two matrices. We can return the AX and AY matrix, so which represent all the coordinates of the X. Remember, we got something from the Voronoi diagram. We got some discretized segments like this, and the two matrices, this Vx and Vy, will give you all the coordinates of the nodes in the Voronoi diagram. And remember that we also discussed a method to represent the graph. So that's the adjacency matrix. So remember, we got the matrix. So by constructing matrix, so if you review our last lecture, you remember that we need to order all these nodes. We need to order all these nodes, and from the coordinates we can calculate the distance between the nodes. So these are the weights corresponding to each of the edge. So by constructing the matrix, so here we got 12 nodes. If we have 12 nodes, then we are able to construct 5 by 5 matrix. So remember that will be 1, 2, 3, 4, 5, and here also 12 nodes. So if we got non-zero entries at a particular position, that means we have a connection between these two nodes. For example, from 1 to 2, we have this link, this edge. So if the distance is given by d1, d1 is just the normal distance between these two nodes in the two-dimensional space. So you already know how to calculate, because all the coordinates are known. So from all these coordinates, you can calculate the distance. So you can put this distance at here. So from 1 to 2, you put this distance. So in this way, you can construct this matrix. So here, if we got only 12 nodes, so you will got a 5 by 5 matrix. So there are totally 25 elements. But remember, in our last lecture, we have an example that we only put 500 random seeds. Remember, we put 500 random seeds. So in this case, we generate roughly 1,500 nodes. If you review our example, you will know, you will understand what's the meaning of this. So you generate so many nodes. So if you construct the matrix in this way, so that will be generating a very huge matrix. So that will be in this dimension. So it's already bigger than 1 million. So it takes a lot of memory in the computer. So typically in the areas of computer science, the graph can be represented by the sparse matrix. So typically, a graph is represented by, the graph is represented by the Laplacian matrix. Laplacian matrix. So typically, this Laplacian matrix are sparse matrix. So the idea of the sparse matrix is just the same, exactly the same as the normal matrix. But the storage method are more smart. In the smart matrix, we only store the elements with a value. So you know in the graph, if you got a graph, so a lot of elements, so actually there are no values because there are no connections. Because in the graph, one node only connects to very limited nodes. So here you got think about your row of a column. It means the connection between one of the nodes to all the other nodes. But in a graph, typically one node only connects to very limited number of nodes. So that means in a row or in a column, most of the elements will be null. Will be actually no value. So in a sparse matrix, only a few elements will be stored with the values. So that's the idea of the sparse and why the sparse matrix are very useful in the graph theory. So in MATLAB, to use the graph matrix is quite straightforward. So for example, if you want to define a sparse matrix, you just declare like this. You declare a matrix as a sparse matrix. Then you just give the dimension, for example, 10 by 10. So that will generate a 10 by 10 matrix. So if you want to put values into a particular value, then the command is also the same as what you did in the normal matrix. For example, you want to put a matrix, the element 1, a value of 10. So you just put a matrix, this J with 2, 1, the index into the matrix equal to 10. So that will, so you only need to take care of the elements with a value. So you don't need to deal with, you don't need to care the elements without the value. So the program, MATLAB program will deal with the other elements. So all the other operations are the same. So the matrix, this sparse matrix, is just a representation of the graph in computer or say in MATLAB. Because in MATLAB, you know, it's difficult to represent a graph. It's difficult for you to tell MATLAB what the graph is. But however, if you convert this graph into a matrix, then it's easier for MATLAB to process this matrix. That's why we require this Laplacian matrix. So it's just another representation of the graph. So they represent the same information. So once you we construct this graph matrix, the next task will be find the shortest path. So you know our task is to eventually to find the shortest path from the starting point to a destination. But so far, we use the Voronoi diagram to discretize the problem space. So we got this kind of nodes, and you need to do something to convert this matrix, convert this graph into a matrix. Then the next step will be to find the shortest path. So the method to find the shortest path will be the dynamic programming techniques. So it's a optimization technique. So far we are able to discretize the problem space, and we are able to represent the graph, the space, the discretized space in a matrix. But the main task is how to do the optimization, how to find the shortest path from between two particular points. So the technique will be very popular, very useful, also a very powerful technique. But this technique is also very challenging. It's quite complicated. So this method is called dynamic programming. So the dynamic programming is a mathematical optimization method. So fundamentally, it's an optimization technique. So you just think about our scenario. Now we have this graph. We want to find the shortest distance path. So we require some optimization technique. So the dynamic programming is fundamentally an optimization method. And it's also a computer programming technique. So it's quite practical. The basic idea of the dynamic programming is to simplify a complicated problem by breaking it down into simpler sub-problems in a recursive manner. So the basic idea is to the basic idea behind the dynamic programming is to simplify complicated problem by dividing into a sub-problem by breaking. Breaking it down into simpler sub-problems. And a more important element here is in a recursive manner. So to understand the basic idea, you can think about the second assignment. So in the second assignment, you know the task. The task is to, like this, we got a pendulum. So starting at the position of 0 and at 0 velocity. So the task is to rotate this pendulum to a particular position. So we want to rotate this one to a particular location with the angular velocity of 0. So in this process, we want to optimize some costs. For example, in the assignment, we want to optimize the errors, the accumulated errors in the process. And in the assignment, you remember that you will solve the problem. You got a vector, a control vector. You got your UK. So this UK contains the U1, U2 up to UN. So you calculate all these control inputs at the same time. So in one time you calculate all these control inputs. But the idea of the dynamic programming is to do this recursively. That means you do this one by one. So in each iteration, you only have one control input. So for example, at the start, you can only calculate U1. So when you at the position, the next position, you only calculate U2. So in the recursive manner. So because it's a recursive manner, so it's very good for the real-time implementation. So in the computer implementation, it's easier to do this in a recursive manner. But however, in this method, because you calculate all this in advance, it's better for analysis. It's better for the analysis of the problem. But to implement this technique is not the best solution because it takes a lot of computation, and you need a lot of time to calculate all the solutions. So it's not good for the real-time implementation. So the dynamic programming is quite practical. The idea is also quite attractive. But how to implement, how to break down the big problem into the simpler sub-problems. So the idea behind the dynamic programming is the so-called principle of optimality. So it's known as the Bellman's principle of optimality. So this principle is also not difficult to understand, but it's very useful to understand the fundamentals of the dynamic programming method. So this principle tells us optimal policy has the property that whatever the initial state and the initial decisions are, then the remaining decisions must constitute an optimal policy with regard to the state resulting from the first decision. It sounds complicated, but it's actually quite straightforward to understand. So we talk about some control policy. So an optimal control policy has a property that the initial state and the initial decisions are not so important. these are the principle of optimality. It's a very important principle. So what's the meaning of, what's the explanation of this principle? So we can represent the principle graphically to show the idea. So graphically, the principle of optimality means that if we are traveling on the optimal trajectory, let's think about a state from x0 to the final state xn, and you got some optimal trajectory. So this principle tells us all the points from the current point to the end point must also be optimal. So this is the idea. So in a graph representation is like this. So think about our state space. Think about our state space. So in a state space, we have an initial state. Initial state is x0. And we have our final state, xn. So if we solve this problem, if we already solve this problem, we will get an optimal trajectory. So from the x0 all the way to xn. So this optimal trajectory is given by this, for example, the xi star. So let's put a star means it's already optimal. So these are the optimal solution. Optimal solution, and this optimal solution gives us the minimum cost, the base star. So we have the solution xi star and then this base star. So these principles of optimality tell us if we choose an arbitrary state xk. So for example, in this trajectory, so although the trajectory is unknown before we solve the problem, but there are definitely trajectory corresponding to the optimal solution. So if we choose an arbitrary state in between, so assume we choose this xk. If we choose xk, then the corresponding cost from the x0 to the xk we assume to be g1 star. These are the costs from x0 to xk. Then the second segment from xk to xn, assume this part to be the g2 star. So obviously we have this base star equal to v1 star plus v2 star, because we just divide the optimal trajectory into two segments. So this principle of optimality tells us, so instead of solving the whole problem from x0 to xn, if you solve the problem from xk to xn, then this segment from xk to xn is also optimal. So as part of the whole trajectory. So that means if you have this optimal trajectory, then if you take any of the state, but you are not, instead of starting from the initial state, from any state, then the remaining part is also optimal. So this idea can be that here. The meaning of the remaining decisions must construct an optimal policy. So it's regarding the state, resulting from the first decision. This idea. So you don't need to solve the whole problem from the beginning. So instead, you can solve the problem segment by segment. So this is the idea. Solve it segment by segment, then the combination are still optimal. So we can do this in a recursive manner. So we break the problem down into segments, then we solve the problem segment by segment. But the problem is the optimal trajectory is unknown. So how to break it down into the segments? So the idea is like this. So we start from the final state. Then we start from the final state. Then we can try to solve the immediate previous state. So we start from the xn, and we can try to solve, for example, this xn minus 1, xn minus 1. So this will give us, for example, a lot of potential solutions. Here. Then from each of the potential solutions, you can solve the next state. The xn minus 2. So you will got all solutions. So you solve this recursively and backwards until you reach your initial state. So hopefully one of the points will be equal to your initial state. So that will be the solution to this problem. So this idea is quite abstract, but we can use a graph example to show this idea. So you will be able to understand this principle of reality. But remember the fundamental idea is to break down the whole problem into sub-problems, so segment by segment. So after that, we can solve the problem by iteration. So we start from the final state, and we do this iteration by iteration. Eventually, we will arrive at the initial state. So that will be able to give us the optimal path. So now we use a graph example to illustrate this idea. So in this example, assume we got a graph. So there are some nodes in this graph. So I just plot it and here. So there are several nodes. So we have so many nodes. So assume the node A is the starting point, and the node J is the destination. And we have so many nodes in between. So these nodes are connected and defined like this. So from A, we have the link to B, to C, and to D. So the weights, also the distance are unknown. So we define the distance. So from the B, we have the link to E, to F, and also to G. So the distance are defined by 7, 5, and 6. So from C, we also got the link to E, to F, to G. So the distance is defined by 3, 2, and 4. So from D, we also got the connection to E, to F, and to G. So the distance are 4, 2, and 5. So in the next stage, the connection from E, we have the link to H, to I. So the distance is 1 and 4. So from F, we got the H to H and I. So the distance are 6 and 3. So from G, we got link to H, to I. So both are 3, 3. So finally, from H, we got the link to the final destination. So the distance are 3 and 4. So assume we have this graph. So the problem, we have this problem. The problem is for someone to travel from the starting point of A to the destination of J. So by traveling first to one of the nodes in this stage, the B, C, or D, then to the next stage, one of the state to E, F, and G, then to H, I, finally to the destination. So the problem is how to find the shortest path. So the problem is how to find the shortest path from the starting point A to the final destination of J. So we can see this problem is quite similar to the problem that we discussed in the Voronoi diagram. So we got all these nodes, we got all this distance. But here we see even we got a very simple graph. Even here we got a very simple graph. But by just plot the graph, it's quite difficult to represent. So that's why the computer we require to convert the graph into a matrix. So if you convert this into a matrix, it will be much more clear. So it's easier for the computer to understand. So the task is how to find the shortest path. We got all these nodes, we got all the distance. So the first method, the traditional method to solve this problem is to exhaustively search the entire graph. Exhaustively search the entire graph, so we can list all the possible paths. For example, you can try to search. You can search all the possible paths and calculate the distance. Calculate the distance. So you know in this path there are a lot of combinations. So for example, you may find the first path. The first path is we starting from A, then we go to B, then we go to E to H, and finally to the destination. So we can decide the distance. The distance is given by this 2 plus 7 plus 1 plus 3. So this gives us a 30. So these are the distance for the first potential path. And you may get another path. So for example, from A to B to E. But at E, we can go to the node of I and finally go to the destination. So you can calculate the distance. So you know there are a lot of combinations, but it's the simplest method. So the concept is very simple. So you just search all the potential paths, and you calculate the distance. Then from this distance, you will know which one is the optimal path. So this is actually the technique that we used before. So in the second assignment, we actually are trying to use a method like this. So you find all the potential solutions, then you compare which solution is the best, which solution gives you the optimal path. But this method is quite computationally expensive. You know this method is very computationally expensive. So it's very, very costly. So this is the first potential method. So another better method is use the concept of the dynamic programming. So we try to use the principle of optimality to find the shortest path. So we try to use the idea of dynamic programming. So remember, the idea of the dynamic programming is to break down a big problem, like here, into the sub-problems. Then you are going to solve these sub-problems one by one. So iteration by iteration. So firstly, we can define distance. So firstly, we define distance function. So for example, we define a function f for a node of x. So this defines the minimum distance from the node of x to the final destination of j. So we define this new function in the first iteration or in the first stage. So we start from the destination. So it's obviously the f j equal to this equal to 0. So from the node to itself, the node to itself, definitely the distance is 0. So this is the first iteration. So it's very simple to understand. So next we working back from the destination. So we're working back from the destination of J. So that will go to the nodes of H and I. So we may have this H. So from the H to the destination, there only one route, and the cost, also the distance, is 3. And from this F for I, so the distance, so the route from I to J is only one route. It's only one route, and the distance is 4. So now we are coming to the second iteration. So next we going further backwards to the third iteration. The third step is to going back one more stage. So in the next stage, we got 3 nodes for the E, F, and G. So for the E, to the destination. So now we are going to calculate the distance. You know this function, this FE means the minimum distance from X to J. So that means the minimum distance from E to the destination. But here we are not calculating this anymore because we already know the minimum cost at H is 3. The minimum cost from I to 4. So we are not explicitly explore this part, but we directly use this conclusion. We directly use this optimization results. So from the E, there are 2 paths, to H and to I. So we can calculate the minimum distance between these 2 routes. So for the first route is this distance, the distance from E to H plus the distance from H to destination. So that will be 1 plus F H. So this is the first route. So the second route from E to I. From E to I, the distance is 4 plus Fi. So we directly use the optimization results from the previous step, from the first step. So it's quite straightforward to understand this, right? So we just use the results from the H and I. So gradually you will see the advantage. So this one is quite straightforward to calculate. So it's 1 plus this FH equal to 3. So this 4 plus Fi equal to 4. So we know this minimum cost equal to, so this 4, this 8. So this equal to 4. So So equal to 4, this is corresponding to the optimal path. So these are the optimal paths. So these are the optimal paths from E to the destination. So this is given by E H, because we are going where the H and to J. So these are the optimal paths from E to J. So we can do the similar things to the next node in this stage. So the other node will be F. So from the F we only got 2 paths. So with the 6 to H and 3 to I. So we calculate the minimum distance with 6 plus FH and 3 plus FI. So this given by 6 plus FH equal to 3. So the Fi equal to 4. So this gives us this 9, this 7. So this equal to 7. So this corresponding to optimal path from F to the destination. So this given by starting from F and where I eventually to J. So now you know the idea. We are using the optimization results from the previous stage. So these are the idea. So we can do the same thing for the next the other node for this G. For the G, we got 2 paths to H, also to H and I. So it's a minimum distance between the 3 plus FH and 3 plus this FI. So this equal to 3 plus FH equal to 3. So the Fi equal to 4. So this gives us, so this 6 is corresponding to the optimal path from G to the destination. So this given by this G to where H to the destination. So now we are at this stage. Then the next iteration will be going back one more stage. So that will be, we can calculate this FB. So FB we got 3 options. FB we got 3 options to E, to F, and to G. So these are given by, so the minimum, there are 3 options. So the first line is 7 to E. 7 plus FE then with 5 to F, and 6 to G. So this can be calculated as 7 plus, so the FE equal to 4. So the FF equal to 7, and FG equal to 6. So this is 12, 11. So we know the minimum cost at here is 11. So the 11 corresponding to optimal path from B to the destination. So this will be from B. So this where E. So this is where E. So we know this actually give us the best solution. So it's where E. But from where E, we don't have the other information about the routes, so we can check the previous step. So we know the optimal from E will be to H and to J. We just copy down. We just copy down the results. So that means in this stage we only determine this node. Only determine this node, and the optimal path from this node to the destination is already known from our previous results. So these are the idea why we can save the computation. So similarly, we can solve the node for C. So from C, we also got 3 options. So 3 to E, and 2 to F, and 4 to G. So this given by 3 plus FE equal to 4. So FF equal to 7, FG equal to 6. So this given by 7. So also from the first root. So this gives us the optimal path from C to E, and we just copy down the roots from E to J. So that will be to H to J. We just solve one node, one stage. So finally, we decide the distance for the node of D. So for the D, there are also 3 options. 3 options for 4 to the node of E, and 2 to F, and 5 to the node of G. So this 4 plus, so FE equal to 4, so FF equal to 7, so FG equal to 6. So this equal to 8, 9, 11, so this equal to 8, also given by this root. So we can determine the optimal path from B to the destination. So from D go to E, and from the E to the destination, the optimal solution is already known. So this where H to G. So now we already solved the second stage. We already arrived at the second stage. So it's called the B, say D. So next we can go to the the starting point to A. So it will be the fifth iteration. So the fifth iteration, we can determine this A, so the F, A from the A to the destination. So there are three options. So the first option is 2 to the node of B, then 3 to node of C, and 3 to node of B. So the FB equal to 11, then the FC equal to 7, and FD equal to 8. So we know the minimal cost given by this one. So it's a 10. So from this we can know the optimal path. The optimal path is given by from A next we go to C. Then from C, how to estimate that we don't know in this stage, but we can check the previous stage. But here we already know from C to D to H to J. So we already know the solution from the previous step. And we also know the shortest distance. So this shortest distance is equal to 10. So computationally, this is much more efficient. So these are the idea for dynamic programming. So for the dynamic programming, for the path planning in a graph, or to find the shortest path in a graph, a special version of the dynamic programming has been developed. It's a very known version of the dynamic programming algorithm, known as Tesla. It's known as the Tesla's algorithm. So it's actually implement the similar idea that we did here, but it already do all the programming and all the analysis. And in MATLAB, there is a special function to implement this Tesla's algorithm. So it's known as the graph shortest path. So you can use this function in MATLAB to solve the shortest path problem. So in your assignment, eventually you will use this function directly, but you don't need to do the programming by yourself. But for this one of the input parameter will be the graph matrix J. So your task is to construct this graph matrix J. Okay, so that's all for today.
他的最后一个只有减3标志而已。一个进来然后人家赶他走了。 哦，因为这我还以为卖给你。
对，我们最大的够肉机的。